Today I'm going to talk about another video as an example and explain step by step how we can use the tutorials that we've had before in terms of vectors and planes and how to use them to create this example of drawing on a surface, on a freeform surface. This video tutorial is quite essential in terms of understanding the principle of how you're going to use a tool, especially in the future, attached, for example, to a robotic arm as an end effector to produce your designs with a robot. In this case, I made it as an example for drawing. So the tool that we're going to talk, and imagine that could be like a pen or a pencil, or it could be a milling bit, for example, in case you want to do a tooling or a milling on a surface, a freeform surface with a robot arm. Therefore, we're using the same components and the commands before that we talked about, like a surface evaluate, extracting the surface parameters and the planes, and how we're going to use them for this assignment. So if I want to show you very quickly here, this is our freeform surface that I just modeled in Rhino. I can show you, for example, you can always change it. Let's say if this is the surface you want to work with and you're satisfied, then you can always edit it, hide it. This is your design. And here we have also another component that we call it as a tool. It's a geometry that it's also made in Rhino separately. You use that in order to produce the shape you want. In this case, the drawing you want on the surface. We are going to talk about a new component that you're going to learn from this assignment. It's called orient. Orient is a command in Grasshopper that we use to change the orientation of a geometry or a shape according to a reference plane. So we give the source plane, which is a plane on the tool, and we reorient it into a new location and a new direction based on a given target plane. So that way we can actually start creating that effect of drawing on the surface. If I zoom in here, I have a slider which I can move, and you see that with slider I'm actually moving our tool on the surface as if it's going to draw the horizontal lines on the surface. So the step by step to get here, you have to understand that we will have initial surface and we will have to create the lines that we want to draw based on. Then we extract the points and the planes from those curves on the surface, and we use those planes as a reference for guiding our tool on the surface. Later, this will be the frames and the planes that you give to the robot to move around, and based on the dimensions that you have defined for your tool, you can produce your design. So I'm going to open up the file that I have uploaded on the wiki. Here all the wires from the components are disconnected, and that's with the purpose, of course. And I'm going to explain how we have to use them, the components, in order to create an assignment. So first of all, we need our initial surface, which is the design that you have. For example, that freeform surface. I have it hidden in Rhino, so I just have to press it to bring it back. I also have my tool here. So I want to start with the first tool, and then I also have another tool example intentionally to also explain that how different shapes of tools require different orientation planes and reference planes that you can use on the surface. Imagine if this tool is a straight axial tool, which could be like a marker or a milling bit. You would have one reference plane that has one vertical, for example, orientation in the Z direction, the normal direction. But whereas on the second tool, you will see that it looks like a L. So the shape is actually changing here with the orientation, and we will have to give a different plane as the reference, which would have a different direction of the normal plane. Instead of vertical, you would see that it will be horizontal. I'm going to go further and explain later, then you will see the difference between these type of tools as examples. And we know that there are countless of different tools and end effectors that later we have, and we have to find out what are those tools as reference planes that we have to use in order to define for the robot. So first I'm going to start with the surface. I define my surface here. I assign it from the Rhino to Grasshopper. That's the first step, of course. And the second step is that I want to define my tool, which in this group of components here, I can assign my tool into the geometry component. So after defining the tool in Grasshopper, it's very important to find the tool's orientation plane. And that's what we're doing here. So I'm going to do it like over here, up here, separately, so you can actually follow. I'm going to extract the plane, the reference plane, from the tip of the tool. And if you pay attention, the tip of the tool is some horizontal surface. And I will end up with a type of plane that will give me a vertical normal from that surface. One way to do it is that if I create a box around my tool with bounding box and explode my box into single surfaces. To do that, I can use deconstruct brep, and I would end up with having a box with multiple faces. Basically, I would end up having my box exploded into multiple faces, lines, and vertices, which are the points. I know that I would end up with 6 surfaces, and I have to just select which one of those surfaces will be the bottom one. So I would find that specific item number index from the list of 6 surfaces. I can preview this off so that I know that, yeah, the first surface will be the one that we don't need. So I'm gonna make a slider from 0 to 6 to look for it. And it will be surface number 4. This is the surface that we want to work to extract the parameters such as plane and center point and etc. It's very important to know that we want the center point of this surface to extract the plane from, because we want to find the center point from the tool mathematically. So I would use that surface to evaluate a certain point on it and use the frame out of it. This is exactly the same as the previous assignment. If you've done it, we use evaluate surface. It gives us the point, the normal direction, UV directions of the surface, and a frame, which will be the plane that we would use as a reference here. So I will just make sure, by the way, to reparameterize the input for the surface, because reparameterize, as I also explained before in the older tutorials, it would create a domain on the surface from 0 to 1. And then we can use this multi-dimensional slider to select which area, which point we want to select on the surface. So if I just connect these surfaces on the evaluate, then you will see that it's automatically selecting the center point, because we are here having 0.5, 0.5. If I put it on 0, 0, you know that it will go to the corner, first corner on the bottom. If I put it on the 1, 1, it will go to the other side of the corner. So it's very basically clear, the direct correlation between the multi-dimensional slider and the point evaluation on the surface. So I'll put it on 0.5, 0.5, center point. That will be our tool center point, basically. And the frame that I want to extract will be this plane that you will also see here. That will be the first, the reference point for our tool. So basically, these are why I had these components here. I can delete them and replace them with these ones. So this is defining the tool and the reference point, the reference plane. Now I go back to my surface again, and this time I'm gonna draw the lines on the surface. I use a contour. It's a command in Grasshopper that allows us to draw horizontal lines, parallel lines, on a certain shape according to a direction. And the lines distance between them could be also predefined as a different parameter here, as you see, for example, number 5, in order to control the number of lines we want. I type contour, C-O-N, contour. It creates contour curves. This is also a same command that exists in Rhino as well. But here in Grasshopper, you can just control it parametrically. So I connect my shape to my surface to the shape. Then the direction, I can always define any direction I want, but in this case, the direction is just a z vector because it's 0, 0, 1, so it goes on the z direction upwards. And the distance, I want my curves to be made from distances of 2 millimeters. So I just give them 2. And then you'll immediately see that there is a bunch of curves, a series of curves made on the surface. If I change 2 to 3, I would end up with less curves because the distances are more, and therefore will be less curves fitting on the surface. So the output from the contour will be 39 curves. And I want to make sure that all these curves, oh, by the way, all these curves which are made are following the same direction. For example, the first curve starts from the left to the right. From the right to the left. The second one follows the same direction, and so on. So all of them have the same directionality, which we will have to also consider if we want to have our tool to be following a certain direction. In the example that I showed you before, we want the tool to start from one corner following the line, and once it's reached to the end, we want it to step up and start the second curve from the other side and following it back to the initial direction, position, but on the first curve. And the same principle, again, starting from here, going to the left, and then left to the right, and this way we can go up like zigzag on the surface. So for being able to do that, we have to select every other curve on the surface and flip the directions of those every other curves, so that we make sure that the first curve, if it's from right to left, the second curve is from left to right, and the third curve is again right to left, and so on. So I'll make sure that I'll flatten this so that I have all of my curves into one list. Then I'm going to select every other curve and flip the direction. That's what we have done here. We will do here. And I'm going to maybe do it separately so that it will be more clear and understandable. I would delete all the in-between components, make it more clear and open space. So I want to select every other of these curves and flip their direction in order to be able to actually have the tool going in one direction and at the end going back. In order to start selecting every other ones to every other curves to flip the direction, I'm going to use item list item, and I want to make sure that first I have my data tree flattened so that I have all the items in one list, and I connect it to the list item here, and it selects the first one for me because by default the number as index is 0, but I want to give it a series of numbers, and within this series of number I'm going to give indications that where I'm going to start and what are the steps that I'm going to take in terms of selection and how many rows should I go for that. So it's very important to know how many curves do we have in the list first, and being able to define these inputs for the series. If I already connect the series to the list, it would just select the first 10 for me because it's by default starting from 0, it goes the steps as 1, and then it goes to number 10. One thing, if you want to start selecting your curves in this direction, list item works in this way that if you keep going and you pass the last number here, it starts again from the bottom, and we want to prevent that because we want to only select these curves once. So I want to make sure that I wrap the item list, because then all the items will be just reached once. It does not go back in a loop. So for starting, I'm going to start from 0, and steps should be 2 because I'm going to skip every curve. Sorry, number 2 goes to step, and if I select it already, you'll see that it skips every curve. And then I want to make sure that I am actually getting it right with the whole list. So for that, I have to extract the number of items in the initial output from the contours, which will be achievable if I use list length. It gives me the number of items in the list, and I will have to divide it by 2 because I'm going to only select half of them. So I divide that by 2, it will give me a number which is not integer, and we have to make sure that it needs to be an integer number because 0.5 does not exist in terms of counting objects. So I have to bring integer, connect output 19.5 to the integer, and it will round it up for me to 20. So if I give 20 to the count, it will make sure that it would go from 0 to the top 20 curves, stepping step number 2, and it will just select every other curve for me. And I want to make sure that these curves, for example, are matching with the direction of the other ones. So these are one set of the curves, and I have to copy paste the same to the other side and select the other set of my curves. And in order to do that, I have to make sure that I don't start from 0. This time I would start in my number series from 1, and I will keep the step number again as 2, and I have to give it a count again, that how many times this has to be selected. But you see that you'll get an error here because it says supplied index too high. So basically we want to wrap this, but then we have more items in the list specified, so it's unable to provide you that number of items in this list. So if we are too big, which makes sense because we had 20 items here and 20 items is given as input here, which adds up to 40, and that's bigger than 39, which are the number of available items in the list. Therefore 20 is too big. We have to make sure that we are actually one less than 20, which is 19. So I subtract 1 from 20 and I end up with 19, that could be used as the count. And then it's possible to extract the other set of the curves in between. So now I have two sets of curves, and I'm going to use one of them to flip the directions of the curve. And it happens by just connecting the output to the curve here. And once I have my curves all flipped, then I'll have to again make the same list with all of my curves in. And for that I will type weave, which is this component, also explained before. And weave allows us to mix two lists of items based on a given pattern. Here the pattern is 0, 1, and that means that if I give the first list to stream 0 and the second list to stream 1, it will weave them based on all these lists mixed and combined with these ones. So the outcome should be a list of 39 curves again, but this time every other curve has been flipped. This is what we also have, like I've set for you guys here to do. And yeah, so the output curves here, I'm gonna use them to extract the planes and the frames from these curves on the surface. So we're going to use again the same components as before, the evaluate surface and extract the planes, and then we can use those planes as targets for the tool. But before, we have to know at which locations we want those. So we want those locations to be on our curves because we're going to draw these curves on the surface. And so here is the set of the component. This group of components will give that to us. I'm going to move it away so that I can explain separately. I want to divide the curves. I want to divide them by length. So therefore, I have to specify what will be the distance. For example, 3 millimeters. And then I'll get the points on the curves. If you check the list structure, the data tree structure, you will see that there are 39 branches of data representing the number of curves, and each curve is subdivided by a number of points based on a given length, which is 3 millimeters. So every 3 millimeter there's a point, and it gives us, yeah, on every curve how many points you will have, which is the number of items in each list, in each branch. So I want to find the locations of these points which are on the curves, but this time on the surface. So I have to evaluate my surface on these points to be able to extract the frames that we need. But if I just connect initial surface here and I give these points here, it would not give us anything because these points are not yet existing on the surface. They are points on the curves that we divided. So we have to make sure that our points will be also on the surface before we evaluate those points, locations from the surface. So we have to use a component called closest points, surface closest point, to be able to project these points on the surface. I can use again the same input from the input from the surface we had, and then in this component we make sure that all of these points now actually existing on our surface. So I will just unpreview the subdivided points on the curves, and here I have three outputs, which are the points, exact points on the surface. I have their distances from the initial points that we given them, and then I have the UV coordinates of the points on the surface. This is what we want to use as the input point here, because we want to make sure that what are the UV coordinates that we want to evaluate on the surface. So if I give this input here, I would end up having my surface evaluated at these certain locations. Now I can use the frame on every location as a guiding and target frame for the tool. That's what happens in the last part. So if I connect my frames to the list here, which is the list item, I can select which specific plane I want to showcase, to show the tool on the surface at which a specific plane, and then use these planes as a target to orient my tool. So I have the information from my tool over here, which is the source plane from the frame evaluated on the tool. I connect it here as a source, and then the geometry to evaluate, to orient, and that geometry is the tool that we created in the start. So when I do that, then I see that if I select the orient component, it gives me the geometry, which is my tool, but this time oriented on the surface. And this orientation is based on these guiding planes on the surface that we created over here. I can preview these off, so then I will see my surface. And with this list item and the slider, I can select at which specific location of my tool. So if I just give it from 0 to the last number, it would just follow the same path that we defined on the surface. And this could be what you actually give as a script to the robot to later draw on the surface for you, or mill out the shape from a block of wood, or for example a solid. Now that we have experimented with the tool example number 1, I'm gonna also quickly just do a tryout with the second tool to see the differences. So I want to make my second tool here. I'll just assign it as a geometry back to Rhino, and I can hide it. So it's very important to know now that we want to use a different reference point to define the orientation of our tool. Something similar to what we've done up here actually, but this time it's a bit different because the orientation is changed. So I would explode my tool with the BREP deconstruct, and I would end up having my tool exploded in multiple phases again. This time I want to make sure that I select the tip surface at the end of the tool. So if I give my faces into the list item, then this time also from 0 to, it seems, 7, I can look for it. So yeah, here it seems just the number 1 is the one that we need, so that's easy. I can hide the exploded BREP. So this is the surface that we're going to use to evaluate and create the center point and the frame again. So I can copy paste the module from the top, and instead I would assign the new surface. So now you see that yes, that plane is now created for us. This plane is more like vertical, whereas the other one was horizontal, so it has a different orientation. And it will be nice to see the difference if I want to use the new tool instead. I can copy paste the end again, I will preview the older one off. So if I go back on the surface here and I change the geometry input, the geometry for the tool input with the new tool, I also have to give the new source from the new plane of the new tool source plane. And then this way you will see that the tool orientation is this way, for example. This is if you imagine that we have different types of tools that we can use, and for example one of them could be L-shaped, and it's very important to know that every time the center point changes and you have to define it. So please make sure that you all go through the assignment and finish it and make your own sort of tryouts with it and play around with the script, because it's going to also help you next week when you come to the lab and we're going to prototype together. And please ask me more questions if you have after this assignment. If there's any part that you don't understand, we can discuss at next sessions together. So I hope you found the video useful, and thank you for your attention and see you next time.